Okay, so for easy physics today, we're going to look at induction stuff. We have a rectangular wires pulled through a uniform magnetic field of 2 Tesla going into the page as shown. So wonderful of them. The resistor has a resistance of a total 20 ohms. So what is the voltage across the resistor as the wire is being pulled horizontally at a velocity of 1 meter per second? And it just enters the field. Okay, so we've got a wonderful formula for this. It is our beautiful formula of our induced electrical or electromotive force. So this guy is going to equal B times L times V. Hopefully you remember that formula. It's the last one on there. So what does this mean? So remember, this guy is basically like voltage. So we're going to figure out what that is equal to. B, our magnetic field is 2. L, our length is 0.4, because it's in meters, of course, and V is our velocity is 1. So that means altogether we have 0.8 volts. So that is the voltage across the resistor. Ta-da! Next one. What's the current through the circuit in the above case, and in what direction does it flow? All right, let's just figure out the number first. Number's easy to get though. V is equal to I times R. We know what the V is. The V is 0.8. The I is what we're looking for, and the R is 20. So we're going to take our 0.8 divided by 20. 0.8 divided by 20. So we get 0.04. I is equal to 0.04 amps. Now, we have to use our right-hand rules to figure this out. So what's going to be happening right now inside of this guy, the B, there is no V, right? Now, when we slide it into that magnetic field, it's going to hate the change, so it's going to resist the change. So your right-hand rule is it's going to want to stick the thumb towards you, out of the page, to do that. Now, when you stick your right-hand thumb towards your face, your fingers are going to be wrapping counterclockwise. So that means the current is going to be going this way, which means that the current is going to be going down through the resistor. Or I guess it doesn't care about through the resistor, but it's going to be going counterclockwise in general. All right. So now for purple, what would the voltage be if it were rotated 90 degrees and pulled horizontally at the same velocity? Okay, well, we're going to do the same kind of thing here. Our sigma is going to equal a B and an L and a V. This time, we're going to have the same V. We're going to have a different L. The L is shorter, though, because it's just going to be 20, right? This one. So times V, which is 1 meter per second. Bada bing, bada boom, bada bing. We get 0.4 volts. Would the velocity have... and that's it. What would the voltage be? What would the velocity have to be in order to maintain, change colors, to maintain the same voltage in part A, but with the orientation of part C? Okay, well, I mean, we can go through the math, I guess. We'll do it mathematically. 0.8 is equal to the same formula, B, which is 2, times L, which is 0.2, times V. We're going to solve for V. So we're going to multiply these together to get 0.4. V is equal to 0.8. What does V have to equal? V has to equal 2 meters per second. You could probably just reason that out, but we want to set it up because they're not going to do it numerically on your AP test. They're going to have it abstractly, so you'll have to solve for some weird numbers maybe. Okay, it's just the one of them for here, so hopefully you had fun doing this. See you next time.